let's go. Let's just go. We had technical difficulties again. And in fact, this talk is not about serialization. And I will talk to you about reflection and metaprogramming. And it is not available in C++20. It will probably be available, maybe be available in C++23, since the committee, the standards committee said that reflection is now their priority, one of their priorities, and probably it will be in C++26. Mere mortals, so we'll be able to use it in C++ in 26 in 2027. And in fact, everything can change entirely. So I warned you, and you can go do other more productive things instead of listening to my talk. And let's go. It's Compile Explorer time. And here we have an example. Let's dive from our life experience. Let's write and hopefully you will see, yes, of course it should be yesterday string. So it serializes what I write directly into JSON. Let's try some other things. What can we do without our universal constant that appears everywhere, and so on. I hope you got the point. I will post a link to the chat. Probably at this point, you already have it. And let's go back to the slides. So what we want to end up with is in this slide. I think that you can't understand it right now, but hopefully you will understand it by the end of the talk. So 2 words about serialization as a context to this exercise. What we want to have some structure with some members and values, and maybe nested structs, and maybe empty values, and maybe empty structs. And we want it to serialize to something like that you see on the right. And you want to use it like this. So you pass a string and an instance of an object, and want to get back a JSON serialized into the stream. So we have implementation as such. We have a serialization helper that helps us to serialize all the different values of different types. We have overload for vectors to represent arrays of values. We have optional to represent nullable values, so we can serialize an empty optional as null. And we have general purpose overload for all the other different values like ints and whatnot. And we have a helper function that will iterate over members in structs. And here, here's the user-facing function that is supposed to be called by users. So we can immediately serialize ints, for example, and we get an int value, which is a valid JSON value. We can serialize strings, which gives us a string, which is also a valid JSON value. We can serialize arrays, which gives us an array, which is, yes, it's to a valid JSON object. We achieve this by implementing our general purpose function like this. We This is basically pattern matching for poor people, poor man's pattern matching. And for Booleans, we serialize it like that. For ints, we just stream the value. For strings, we stream quoted contents of the string. And otherwise, we assume that we have a structure or class or type that is not int or whatnot. And expect that it will iterate over members and output each member. So we want to write a structure like this and just call serialize and want to get our JSON. But at this time, we got an error that says that there is no iterate members function. This happens because, in fact, we make a visitor that calls print inside it and pass this visitor and the value itself to iterate members function that we are somehow supposed to implement. And inside print, it does some necessary things. Among those things are outputting a name and the calling print value to output the value itself, one of the members of the struct. So what would you write is, in fact, something like this. We have to implement iterate members function, which will, well, iterate over members and call visitor on each member. And eventually we can get something output like this, a JSON. And this saddens me. This is very sad for me. And what can we do? Let's see what reflection offers to us. In reflection, there are many weird things, but the central piece, I think, is meta information, which is an entity that reflects some other entity from the code you wrote, or maybe not. We'll see later. And so, other than that, we have a refl expr operator that reflects an entity. So it gets meta information for that entity. In this example, we have a value, a variable value. We, with help of refl expr, get a meta information for that variable, and then we can check if this entity that we are reflecting on is named and can print its name, and we get output like that. We can reflect not only variables, but also types, and in this case, we reflect on type, and eventually this code will output the name of the type, which is int. Great. What else can we do with reflection and meta information? We can compare meta information entities or pieces of meta information, and we can replace our same meta call with comparisons with different meta information pieces like this. Maybe one would argue that this is more readable than this. Okay, let's go further. What else can we do? We can count data members that are present in the entity that the meta information reflects on. And this is really simple. We just iterate over the members and just increment our counter and eventually return our counter. This is a constable function, an immediate function. And in fact, this is already a little meta program, which will we return later a bit. So I was told that, in fact, it should be called data members of, but currently it is not yet implemented. Let's go further. We can apply that metaprogram that counts data members to our struct like this, and we get output with the name and the number of members it has. The next thing is so-called verifiers, which unreflect what is reflected by a piece of meta information. So in this case, we have a variable value. We got meta information called info by the help of referral expert operator, and we can unreflect, so reify the entity that is reflected by the meta information. So we get back in our source code as if the entity, the identifier that is reflected by the meta information. So in this example, we just get back our variable value identifier that is reflected by our meta information info variable. And this is the same as if we wrote just value. And here we have another verifier, which is called unqual ID for unqualified ID. And we can supply to this operator any constant time string, and it will bring into existence an identifier with that name. Unqual ID can be used not only by itself, but also in expressions. So in this case, we have a widget which has some member bar, and we in an expression that outputs its value, we just call unqual ID bar next to w dot, and this is the same as if we just wrote bar. Here are some other verifiers. Type name brings into existence a type that is reflected by the meta information. So this is equivalent as if we wrote int. Value of brings into existence a value of constant entity, constant variable, and this is similar as if we wrote 23. Otherwise, to work with templates more easily, we have temple arc, which, depending on the actual definition of the template, brings either type in case the template wants a type, but unfortunately this does not work currently. And otherwise, if it's a variable, a value, it brings a value as if we called value of. So it took me 6 months to realize that we can write this even without metaprogramming to convert name values into strings. But yeah, I wanted to use for const export, which we had a proposal for, but in fact, I was told that it is called now template 4, which does the same thing. And unfortunately, it doesn't work. But who cares? We can do it other way. So here we have a metaprogram, an immediate function that counts the number of members that are in our enum enumeration. This is very simple, I hope. We get a reflection of our enum type. We iterate over its members, count, and just return a value. This function returns the name of the nth member. So this is, I hope, also very simple. We say which member do we want to get the name of. So we iterate the n times. and over the members, and just return name of the currently pointed to member. Next, we want to have this helper function that will, with the use of magic of template metaprogramming and fold expressions, give us, will compare in the fold expression all the members, and when it finds, when this expression becomes true, so when we find the needed member, we just assign it to our name variable that we return, and this expression with comma operator, with help of comma operator, becomes true, and it short circuits and exits. Otherwise, it will evaluate to false, and it will continue to iterate over members. So here is our user-facing function. We define a concept enumeration that will match only with enums, and we use it to constrain our input parameter, input type of the input parameter, and we define index sequence from 0 to number of members -1 with the help of widely known facility, I hope, and call our helper function, which will hopefully return the name of the our argument that we got. And so we finally can write something like this, and we got in outputs our 1, 2, 3, and finally the problem of C++, which is the holy grail of all the problems of C++, is solved. Finally, C++ can become a normal language. So this is great. But what about serialization? In fact, we can use the same approach, and we can what you want to write is this. So using template 4, you iterate over members and just call visit on all the members. But unfortunately, this doesn't work, and we can use the same approach that we use for the enum case. We use our data member count that we defined before. Next, we want to be able to get member names for nth member. This is fully analogous to the enum case. Next, we define our helper function, in which we, with help of the fold expressions and comma operator, iterate over all the members. And finally, this is our user-facing function, which is used by serialization. And here we again define index sequence for all the members and call our helper function, and which will call visit for all the members, supplying the values and names. And now we can finally just write our structure and call serialize, supplying stream and an instance of that type. We don't have to write iterate members for every structure that we want to serialize. And finally, we get our desired output, the JSON output. Okay, next to metaprogramming. I spent too much time on this slide. Metaprogramming adds injection, fragments, and metaprograms. Let's see what injection is. Here's the syntax for injection. So we want to use minus greater or arrow operator to inject whatever meta information entity, and we can do that inside the constable context. So, for example, we can have a variable in one namespace and we want to duplicate that definition in the other namespace. We can just inject a reflection of that variable in the other namespace. And this is the same as if we wrote int value equals 42. So just copying the definition from the other namespace. Fragments. What are fragments? Fragments are like snippets of code that you want to inject into source code by means of metaprogramming. So here is the basic block fragment. We can inject it, or we can, without storing it into intermediate variable, just inject fragment in line. Here you can see an example of fragment injection, and this is the same as if we just wrote a variable, the definition of the variable and initialization. So this is useful. This is useless, in fact, but just an example. Here you can see almost the same example. So we, in our constable context, want to inject a fragment, which is just a variable with initialization. And we can do that inside the function. And after the constable block is evaluated, we can immediately use that injected variable. Here, we can do it differently. We can define an immediate function, constable function that when executed, inject fragment that injects a variable. And in our function foo, we can just call that metaprogram from within constable block, and it will inject the variable, and we can immediately use it. So next, unquote operator. We can write something like this. We can, in our constable function, reflect on type, store it in the intermediate variable, and want to use it in the injected code. But we cannot, in fact, use it like this because this is kind of confusing, because we are injecting this code into the source code, so to speak, and we don't know, the compiler in general doesn't know which info is referring to. Is it does it refer to some global variable, or does it refer to the variable that we defined in our constable function? So we have to use the unquote operator. So here we get to the realm of constable, statically evaluated, compile time evaluated code. And in that code, we inject a source code, so to speak, that will end up in the code that will be executed at runtime. But in this injected code, we want to unquote the variable that is defined in the compile time realm. So for this purpose, we need the unquote operator. So this is not confusing to the readers and to compilers. Let's return to fragments. We have requirements for fragments. In this example, this is a requirement for type T. It works something like that, when we inject a fragment, when we define a fragment, it doesn't know, it may not know about some types that may be not even defined to that point. So we want to constrain that when we inject this fragment, there should be a type T. And so this code that we inject should be valid, should use that type T that is present at the point of injection. And we end up with valid code. For example, here we define the fragment. We then defined our type T, and only then we inject our fragment. It finds the type T that we require, and we can write output stream, and we can get an output like this. Otherwise, we can require an identifier. We have to specify exactly the type and name of the identifier. So at the point where the code is injected, it must find that identifier, and then we can inject the code itself, and it should be correct and should work. In this example, we define a fragment, then we define our identifier, then we inject the fragment and can immediately use the injected identifier. We can get an output like this, which is cool. So other fragment types are, besides the block fragment, are namespace fragments, class fragments, which are used, by the way, for metaclasses, and enum fragments. Let's see what they do. Here is an example of a struct fragment or class fragment. They differ only by default visibility. So in this case, all our injected members are visible by default. And notice that when we define the fragment, we don't have to know the type beforehand. We just define a placeholder name, in this case T, and we can define all the members in terms of that placeholder name. In this case, we delete all the copy constructor and copy assignment operator. So we essentially make this type non-copyable, and we can write something like this. We just write a struct, invoke a metaprogram inside the constable context, and what we get is a type with deleted copy constructor and copy assignment operator. And we can write static asserts, and that will ensure that we get exactly what we wanted. Now we can make movable another metaprogram or constable function, if you will. In this case, we inject a fragment, a struct fragment that enables default move construction and move assignment. And now we can write our movable but non-copyable type by invoking make non-copyable and make movable. And in this case, we get something like this. Notice how much typing we saved. This is, in my opinion, this is awesome. So in our fragments, the next topic, we can implement a less error-prone way to define bitmask enums. In this case, we have our helper function that injects a concrete member with concrete name with concrete value. And to use that, we define our user-facing function, meta function or constable function or immediate function that iterates over all the names that the user supplies to us and defines members, enumeration members with that exact names, but with set bit offset one place each time, if that makes sense. I hope this makes sense. So essentially, we iterating over the supplied arguments, which are names, which are constrained by the requires and immediately defined concept. We iterate over that names in fault expression using comma operator. And essentially what we do is we inject, for each name, we inject a member with the value defined by the expression 1 shifted by the counter. So we can write something like this. we want to have, in this case, 3 members that each have bits in different places. And we end up with something like at the bottom of the slide. And we don't even have to write some additional members, because the trailing comma is permitted. This is valid code. Okay, namespace fragments. They can help us to define bitwise operators for our strong enum type, because without them defined, you cannot apply bitwise operations to the enum types. You have to static cast them every time, and we want to ease our lives. So this meta function injects bitwise OR and bitwise AND operations for our specified type enum, and we can use it. Yes. So essentially, what we do is we copy paste this code into our desired place, and we replace enum with the specified type. So what we have our enum, we can call our meta function, invoke our meta function in the desired place, specify the enum type. And now we can write something like this. So we can write one enum member, or bitwise, or another enum member. Or we could write AND to check if this value we got has bits set in one of the positions. Okay, let's go back for a bit to the problem about converting enums to strings. With metaprogramming, you could write it like this. So we have our compile time evaluated code. So it's statically evaluated code. Const eval block. We want to inject for each member code that compares the value of the member to the value that we got in our function, in our runtime function. So we write, we have to write requires, because we want to refer to the our local, so to speak, variable that is the parameter of this function, of the runtime function, outside of this compile time block, const eval block. And next, we inject some code that will be evaluated, that will be executed at runtime. And of course, we have to unquote all the things that we use from the const eval block. I hope this makes sense. Unfortunately, this doesn't work. By this point, I think you got the recurring demo of this talk. But anyway, we can do it just a little bit differently. We can define our const eval block like this. We, instead of requiring the variable, we get a reflection of that variable. And in the code that we are going to inject, we just unquote that variable and get its value injected into the code that will be executed at runtime. So, okay, what about serialization? What you want to write using metaprogramming is something like this. So again, we have our const eval block, in which we require the visit and the value variables that are our parameters of our runtime function. And we want to inject this code that visits each member. And of course, we have to unquote the member variable that is from the const eval block. Unfortunately, this doesn't currently work, but we still can make it work. So we just, again, instead of requiring our variables in the const val block, in the injection fragment, we get the reflections and just unquote those reflections in the injected code. Okay, if I manage to interest you in this kind of thing, you can go right now to cppx.godbolt.org and try it out. Thanks to Matt Godbolt for hosting that prototype at his platform. If you want to get some theory, though dated a little bit, you can go to the talks by Andrew Sutton, one of the authors of the proposal and the prototype I'm talking about, and watch his talks. And yeah, this is the end of my talk. I want to thank White Childers for his feedback. He made my slides and code a little bit better and answered my questions. Thanks very, very much. And yeah, I think I have to go back to the realm of runtime code, and allow me to do it just a second. Oh, that's better. So I see we have no questions, so I have bonus slides. Let's talk about metaclasses just a little bit. We can define a meta program like this. In this case, we have to receive meta information that reflects the type we're applying our metaclass to. And when we apply our meta function, like you see in the middle of the slide, we get our meta function executed at compile time, and it can. Okay, we're back. So the idea is that you get the reflection of the type that was written in the source code, and you can transform it into almost whatever you want. You can modify members, you can omit members, you can add members. And in this case, we add a member of type string with name text. And here is another meta class that kind of turns what you write into an interface. And here we iterate over members. If we have a data member, we say that we don't allow data members. If we have a destructor, we make it virtual. If we don't have a destructor, we add a virtual destructor, virtual default destructor. And otherwise, we make all the non-virtual, non-pure virtual members pure virtual. And we get something like this. We can define a cat that we want to become an interface, and we get as a compiler output something like this. And I think we have 15 minutes for questions. So I see no questions in the no questions asked. So either everything is clear or nothing is clear. I hope that everything is clear at this point. Okay, so far no questions. Please catch me up. Catch me after the talk. I will try to hang out at this room in the lowest floor. I will try to find empty table, and you can join and ask questions. You can find the slides here at the bottom of the slide. So I guess that's it. Oh, we got question. Okay. What compilers can we use this code in? By Claire McRae. So you can go to CppX. Excellent question, by the way. You can go to cppx.godbolt.org and you will be able to use it online. Otherwise, this is developed by Log3, Andrew Sutton's company. They just moved to GitHub. You can find them at github.com/log3/meta. And there are instructions, there are wiki, there are tutorials, though not that expensive as one would want. And you can just clone that repository, and there are instructions to build it on different platforms. And yes, I just did myself. I cloned it and built it and use it locally. But you don't have to. You just can go to cppx.godbolt.org. Okay, catch me at this room at the lowest floor. I will be there. I'm eager to answer questions, to contage you with this stuff. So I think that's it. Thanks for watching.